Okay, well, we have another theorem, which is Cauchy's mean value theorem, which is similar to the mean value but applied to different function. So suppose f and g are continuous in the closed interval ab and differentiable in open ab. Then we have a c in this open interval such that f at b minus f at a times the derivative of g at c is equal to g at b minus g at a times the derivative of f at c. Okay, so it's kind of an extension of the mean value theorem. The mean value theorem is actually a particular example of this more general theorem. Okay, and you can prove it using Rolle's theorem, applying Rolle's theorem to this function. Okay, and again you have to check that h at a is equal to h at b, and that is differentiable in the interval, continuous, and so on and so forth. And then you will get to this formula. Okay. But we mentioned Cauchy's mean value theorem because it is an important element in the proof of this rule that all of you know, which is L'Hopital's rule. Okay? And it is an important tool that we have in order to compute limits using derivatives. Okay? So it says, suppose we have f and g, two functions, such that the limit when x goes to a of the fraction, the quotient between the derivative of the two functions is some value L, right? Well, if the limits of f and g are both 0 or plus or minus infinity f at a, then that means that we have an indetermination, right? Because we have the limit when x goes to a of f divided by g is either 0 by 0 or plus infinity, or minus infinity, right? It's one of these possibilities. And this is an indetermination. We don't know how to solve it. Well, L'Hopital's rule says if this is the case, then this limit is the same as the value of the limit we obtain with this. Okay? But provided that this limit exists. And this is important because in some cases it will not exist. Okay, so let's see some examples of this. Okay, for instance, we have the limit when x goes to 0 of the sine of x divided by x. We know that this is going to be 1, but this is just 0 divided by 0, right? So applying L'Hopital's rule means that if we compute this limit, the limit of the derivative, okay, and this exists, and in this case this limit is 1, right? Then this limit is exactly the same as this limit. Okay, so it is only because this limit exists. We're gonna see later an example in which this doesn't work. Okay, so for instance, compute the limit when x goes to 0, e to the x minus the cosine of x divided by the sine of x squared. Well, again, this is going to 1 minus 0 minus 1, 0, the sine of x squared, 0. Okay, so now we need to compute the derivative of the numerator. So this is e to the x minus 1 plus the sine of x divided by, and then we have 2x. Okay, this is the chain rule. We have the derivative of this times the derivative of the cosine at x squared, right? And now we have, this is 1 minus 1, 0 plus 0 divided by 0. Again, the derivative, 0 divided by 0. Well, we have to compute the derivative again. So this is e to the x plus the cosine of x divided, and now we have 2 times the cosine of x squared. Now we have the product rule, plus, and then 4x squared sine of x squared. Sorry, minus, because the derivative of the cosine is minus. And now we have, this is going to be 2, and then this is going to be 2 minus 0, 2, the limit is 1. Okay, so now we can say that this is equal to this. So this is, I'm not doing it very rigorously because we don't know if this is equal to this unless this exists, and we don't know if this is equal to this unless this exists. Okay, so if you get to something that doesn't exist, then these equalities would not be the same. Okay, so just have that in mind. Okay, so you can use L'Hopital's rule to prove these asymptotic equivalences that we have seen before, right? So 1 minus the cosine of x is asymptotically equivalent to x squared over 2, which means that the limit when x goes to 0 of 1 minus the cosine of x divided by x squared divided by 2 is 1. So we can compute this limit using L'Hopital. The same thing with the tangent in x, e to the x minus 1 and x, the logarithm of 1 plus x and x, and then 1 plus x to the alpha, approximately equivalent to alpha times x. This is new, we haven't seen this before, so it's an important one. You can prove this using L'Hopital's rule, okay? And this is an important remark from the definition of limit that we have seen, right? The limit when x goes to infinity, for instance, of f of x is the same as the limit when n goes to infinity. This is a typo. The limit when n goes to infinity of f at n divided by g at n, right? And so instead of, because we have this sequence xn equals n is a particular sequence that goes to infinity, okay? And we know that if this limit exists, that means that all the sequences that go to infinity have this limit, okay? So n is one of those sequences. So that means that we can apply L'Hopital's rule to sequences, to limits of sequences as well, okay? And in particular, we can use this as a variation instead of Stoll's theorem, okay? Okay, so now let's see one example in which L'Hopital's rule doesn't work. Okay, so suppose we have this limit. The limit when x goes to 0 of x squared times the sine of 1 over x divided by the sine of x, right? Now we know that the sine of 1 over x when x is very small, sorry, not the sine of 1 over x, the sine of x, when x is very small is approximately equal to x. So this is the limit when x goes to 0 of x squared times the sine of 1 over x divided by x. X squared and x cancel out, so then you have the limit when x goes to 0 of x times the sine of 1 over x, which we know is 0 because the sine is bounded and x goes to 0, right? Now we try to compute this using the L'Hopital's rule, okay? Well, we differentiate the numerator. We have 2x, sorry, the sine of 1 over x, and then we have minus 1 over x squared times x squared gets 1, and so you have the cosine of 1 over x divided by the cosine of x, right? But now this denominator is going to be 1, right? This is going to be 0, so you have the limit when x goes to 0 of the cosine of 1 over x. This limit doesn't exist, okay? So we can't say that this is equal to this, okay? And so that's a very important caveat when using L'Hopital's rule, and a very important limitation of it as a technique. And how to say this, that this is not an infallible technique in order to compute limits. Whenever you do this and then find that the limit doesn't exist, then you can't deduce from it that the original limit doesn't exist, because it does, as we have seen here, okay? And so as we will see in the next unit about Taylor expansions, I think it's a much more sensible approach to computing limits to use Taylor expansions, which is an extension of these asymptotic equalities, but in a much more organic way. And it's a more general technique than L'Hopital's rule. It always works, it never fails, and it's not, I feel it's much more interesting, but we will go into that in the next lecture.